Assalamualaikum everyone. My name is Nur Najiha together with my group members which is Anas Nazmi and Angel. I'm gonna present the geological interpretation of Bundi field using Petrel ENP software platform, and we are from group 2. Here is the table of content. We will start with overview of Bundi field and followed by the project outcomes, workflows, methodology, discussion on map, interpretation, conclusion, and also reference that we have used for the session. So first thing first, we will present about the overview of Bundi field.
Now I'll be talking a bit on the overview of Bundi field. Bundi Well and South Bundi Well are both located within Malay Basin northeast part, and these are the information about the Malay Basin. It is considered as shallow water. The tectonic events that lead to the formation of Malay Basin include the extension during late Cretaceous to early Miocene, thermal subsidence during early Miocene to middle Miocene, and the compression during late Miocene to Pliocene. The Bundi and South Bundi field resulted by combination of structural events that took place during the extensional and compressional processes. They are both gas fields. Bundi 1 well and South Bundi 1 well are located in north-northeast direction from Kemaman supply base Terengganu. Bundi 1 is drilled as a deep well test to examine the porosity evolution in the basin margin position on strike, and South Bundi 1 is drilled to test the hydrocarbon potential and reservoir quality of groups E, F, H, and I of sandstone group that has been found to be the hydrocarbon bearing in Bundi 1 well.
However, during the exploration process, both wells are terminated shallower than the predicted end in the planning, mainly due to the presence of severe abnormal pressure. It occurs when the burial and sedimentation rate is high during sunrise phase at the center of the basin, resulting in the development of disequilibrium compaction and later lead to the overpressure. Other factors such as the lateral transfer of the excess pressure into the permeable rocks cause the overpressure generations in the basin flanks. On the right side is the examples of group that exist in the Malay Basin, such as top E and base E, top I, base I, and top K. So in my left side of the slide is the stratigraphy of Malay Basin from unit A to M with different lithologies and structural history, while our group has been assigned with unit E32 sandstone with the age of late Miocene and composed of sandstone interbedded with shales and siltstone. The depositional environment of sediments is fluvial or estuarine channels area cultivated with erosional unconformity, while the thickness is 370 meters in Bundi 1, while it is 399 meters thick in South Bundi 1. The environment setting is made up of channel and point bar sandstones deposited in lower coastal plain environment.
There are several project outcomes which we are able to achieve through the process of using Petrel ENP software in executing geological interpretation of Bundi field, such as produce seismic well tie between 3D seismic data and well data from Bundi field, perform horizon and fault picking on the seismic section, generated subsurface map through correlation of seismic data and well data from Bundi field, and generated time and depth domain map of the E32 sandstone horizon. And lastly, we interpreted the geological structure of the subsurface in the Bundi field.
Thank you, Najiha and Angel, for the introduction and the project outcomes. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Anas Nazmi and I will proceed with the project workflow throughout this semester. So, we use almost 12 weeks to being introduced in the Petrel software and start to practice with it and become familiar with the tools in the software before we can start to interpret the section. So we can see at the methodology section, we use almost 7 weeks to import the data, to calibrate the well and the section, and also to pick the horizon and the fault before we can convert it into the surface map, and then we can interpret and discuss about the geological features of the Bundi wells, and lastly we can submit the video presentation and also the poster. Now I will proceed with the methodologies that we use throughout this project by using the Petrel software. The figure above shows the methodology that we use in this project and by using the Petrel software. So we have been provided with the well data, which are the well top and well heads data, well logs data, and also the check shot data, and the seismic data, which is in the file type of SEGY, and also the inline and crossline data. So with this data, we import to be a file in the Petrel software, and then we calibrate the seismic and also the well data before we can proceed with the interpretation and also the fault and horizon picking. So for our group, the horizon that we choose is the E32 well top, which we interpret and we pick the inline and crossline with 50 units interval before we can proceed with the stratigraphy interpretation. For the fault, we also use the 50 interval, and we found out that we have 7 faults in our section, and then we proceed with the interpretation of the fault structure and also the other geological features in the Bundi section well. So from the picking, we use the data to convert them into a surface, and we come out with the time domain surface map and also the depth domain surface map. So the time domain surface map is in the two-way time, while the depth domain is in depth, when we use the velocity model to produce the depth map. And from that, we can produce the 3D and 2D model before proceeding to the next interpretation step, and also we can see the section in overall, and we can understand more about the section of Bundi wells. So this is the overall view of the Bundi well section. So we can see in this slide is the surface map, the Bundi well, and also the sub Bundi well, which is separated by a major fault, and also the distance between them also about 4,700 meters. And from the seismic section also, we know that the Bundi well section seismic is very low in amplitude and also the frequency. So for in this Petrel software, we can change the color to be more brighter so that we can easily pick the horizon and also interpret the well top. And from that also we can see the E32 well top, which show that this horizon that we pick and we interpret throughout this project. So this picture shows how we pick the horizon and also the fault within the E32 well top. So this is the 3D section of the fault picking. We can see the picking line and also the picking line of the inline and crossline section, and this is the E32 well top. We can see the dots is indicate the line that we have picking, and also this line also shows the fault that Bundi well section have. So this is how we pick the fault and the horizon. So fault, we know that this is the basic deformation induced structures in the seismic. So from that we pick the fault and interpret it between 25 to 50 increment so that it will be more accurate. The lesser the increment, the more accurate that we can get for the fault. So for the horizon picking, there are many methods that we can use to pick the horizon. We can use the manual and also the auto pick. So for this practice in this project, we use manual picking to pick the horizon with the increment of 50 units. With the manual picking, we know that we have to be more careful in the picking, because if there is a mistake in the picking, there will be the flaws in the map that will be produced. So before we produce the map, we run the quick check of the picking, and we corrected the mistake in the picking before we start to interpret the section. Next, we will proceed with the discussion of the finding in the map generated in our operator software.
So on this slide is our well section from the result. On the left side is the Bundi one, and on the right side is the South Bundi one that is generated earlier in this project before we do the fault horizon picking. It displays well logs in a specified order with the available logs and well. The distance between a well top E32 at Bundi 1 and South Bundi 1 is 4,104 meters. And from the well section, we can see that both logs show the pattern of normal zero phase wavelength. Well, this is the synthetic generation of our Bundi 1 and South Bundi 1. And synthetic generation is actually the fundamental function to link between well data and seismic data. It is a primary tool that allows geological peaks to be associated with reflections in the seismic data. However, due to the sum error, the synthetic cannot be generated in the Petra. So we have generated two types of map in Petra, which is time domain and depth domain. I will start with time domain first. So we can see 2D surface map and 3D surface map plus fault picking on this slide that is generated after performing the horizon and fault interpretation. On 2D surface map, we can read the scale bar, the north arrow, and also the legend, which show the elevation time that is increases towards the east direction and decreases towards the west direction. It is because red color indicate the highest time elevation with the value of negative 1300 millisecond, while purple color indicate the lowest time elevation, which is negative 1725 millisecond. It also counted at 25 millisecond intervals to get a better resolution of the surface structures. And on 2D surface map, we can only see 5 faults instead of 7 because another 2 faults is below the marker of E32 sandstone. So we also have measured the dip angle, azimuth angle, displacement, length and height, also type of each fault that we have found on the seismic section. And I will take the example of fault number 3 that indicates the red fault on the 3D surface map. It shows the measurement of dip angle of 37.2, azimuth angle of 99.83, that has the type of normal fault, displacement of 63.3876, length of 3273.63, and height of 9,310.56. So this is the front view of 3D surface map plus fault picking. And on the next slide, we can see the side view, upper view, and also lower view of 3D surface map. From this 3D surface map, we can see the fault length is range from TWT of negative 1300 to 1725 millisecond. And as you can see, the dotted vertical lines indicate the fault planes. And overall, the 3D view shows a better image and wider angle of the surface map as well as horizon and fault picking on it. So this is also the 3D surface map but with fault surface in time domain, and that will show the shape of fault, either it is flat or curved or any other shapes. The color light on each fault also indicate the elevation, with red region having the highest time elevation while the purple region having the lowest time elevation. So the highest elevation is negative 1500 millisecond, while the lowest elevation is negative 2500 millisecond. This is the side view of the 3D map, and this is the lower view of the 3D map.
I will proceed with the map in depth domain. So this is how the depth domain map looks like. So this is the 3D section, this is the 2D section. From the 2D section, we can see that the elevation is increasing from west to east, and also we can see the fault structures in this section also. And why we produce the depth domain map is because the depth domain map is more accurate than the two-way time map. So with the accuracy of the depth, we can interpret more accurately the seismic section, and the good quality of the interpretation will be produced after this. So this is some of the picture that we get from the battery software. This is the side view of the depth domain map in 3D window. This is from the upper view, and this is from the lower view of the section. This is the front view of the map in 3D section, and this is also the 3D section of the map with the fault also being converted into the fault plane. You can see the side view, the upper view, and also the lower view of the 3D section. With that, we continue with the structural interpretation of the Bundi well seismic section.
Okay, we will move to the interpretation part. The first one is the structural interpretation. And the first one is fault that can be seen as a point of discontinuity of the reflectors of that displays at the adjacent fault block, or the fractures between two blocks of rock. So when there is apparent displacement along the dead plane and slip direction, fault will be peaked on that section. It can also be identified by looking at the abrupt changes in the oases, fault shadow, and associated faults are set. So as shown by the example at the interpretation window in line 781 is the categorized as the normal fault. We can see that hanging wall is moving downthrown while the foot wall is moving upthrown, that indicate by the orange arrow. We can also see the fault shadow, which help us to find the fault on the seismic section. Other than that is the termination of reflection and also abrupt change in depth. So the fault that we found earlier on the interpretation window can also be found at the time slice, specifically at the -644 location, which used to determine the deepening of the fault by looking at the stride and the direction of the fault. So for example, on the first fault, we can see that the stride direction at the red mark show the direction of northeast southwest, and the deep direction that is perpendicular to the straight direction, which is southeast and northwest. So we determine to do the picking at the inline location. So the second structural interpretation is related to faults that is developed due to the formation of rocks called plastic. Its strata are compressed and shortened, resulting in wave-like formation consisting of crest and trough. Faults is measured by the stride and dip of axial plane as well as trend and plunge of hinge line. It is valuable economically because it proves the presence of hydrocarbon traps. So in anticlines, oil will migrate upward towards the crust within the reservoir rocks and becomes trapped underneath an impermeable cap rock, thus becoming a hydrocarbon trap. In seismic also, such trap would appear at the top of the fault structure and is characterized by a high negative amplitude formed by the impedance contrast between cap rock and the oil-saturated rock underneath. So fault is categorized into anticline and syncline, that is arc upward and downward respectively. And in decline, all the rocks are located in the center of the fault, limbs deep away from the center, such shown in the figure below, while syncline is the younger rock are located in the center of the fault, limbs deep towards the center. So we have found folding at the location of inline 948 in the interpretation window. The syncline can be seen like U-shape, while the anticline can be shaped like concave upward respectively in the section below. We know that amplitude will range higher in this region compared to the surrounding layers, and also is predicted to have intrusion of igneous rock beneath the anticline. Wheels in the folding on the time slice will show the concentric circle pattern. Syncline will have a larger shape compared to anticline. In the 3D window of the location -3604 time slice. So the next structural interpretation is related to graben, which is the depressed bulk of the crust of a plane supported by parallel faults. So we have found graben at the location of inline 500 in the interpretation window of seismic section, and the graben is formed when the normal faults of opposite dip occur in pair with parallel straight lines, such in the section above.
Now I'll be presenting on the part stratigraphy interpretation. Reflector termination, also known as lap out, indicates stratal discontinuities which separate system tracks and depositional sequence from one another. The types include truncation, top lap, on lap, and down lap, which is also known as base lap. The example found in the section here is base lap. As you can see here, the yellow color indicates the termination of boundary. And both on-lap and down-lap terminations are in west-east and east-west direction respectively. And here in this slide we can see the sequence stratigraphy. We have a total of 7 sequence stratigraphy here, with sequence T being the shallowest and sequence Z being the deepest. Sequence stratigraphy is the study of rock unit within a chronostratigraphic framework of repetitive genetically gradated strata bounded by surfaces of erosion or deposition or their correlative conformities. It can be identified by observing the changes in amplitudes and frequencies in the section. Next, we have pitfalls. Pitfalls is one kind of abnormal anomalies which can lead to failure in drilling and exploration if we misidentify them. It can be caused by geometry, velocity, or processing. And here at crossline 1859, we can see the example of diffraction which associated with geometry.
Now, I will proceed with the channel and hydrocarbon potential in Bundi field. This is some of the channel features that we managed to find in the Bundi well section. So the blue circle is the mindering type of channel, while the red circle is the anastomosing type of channel. So in the seismic data, we can identify the channel based on the depression basin like features shows in the seismic data. So from this we can see that this is the channel present in the Bundi field, and we know that the channel of the river is indicating the good type of reservoir, which consists of sandstone with high porosity. So this locality, we can say that we can assume that this locality have the potential in containing the hydrocarbon and become a good type of reservoir in hydrocarbon exploration. Bright spot is the one of the hydrocarbon indicators. This is because hydrocarbon shows high amplitude in seismic attribute anomaly, and from that we can indicate and the presence of the hydrocarbon. So most of the bright spot in the Bundi field section is associated with the fault. So we can say that the fault is becoming the good trap for the hydrocarbon, which we can call it as the structural trap. So we have come to the conclusion of this project. So the first one is the seismic interpretations by using better software can be done with full range of views because of the various tools provided in the software. Next, the complex structure and stratigraphic features are the challenges that need to be observed and interpreted carefully by us. Then, the horizontal picking is crucial for producing the time and depth surface map for overall views and overall understandings before we can interpret the section. The lower the increment of picking in the cross line and the inline, including the fault also, will give the better resolutions of the map and also increase the accuracy for our interpretation. And the last one is the seismic interpretation needs high patience and precision in order to get the best result and come up with the best outcome for the hydrocarbon exploration, especially in the oil and gas industry. So that's all from us. Thank you for your time and stay safe.